Test, test. Je ne peux rien dire. Est-ce qu'on m'entend bien? Ouais, surtout qu'il n'y ait pas le bruit de fond. Test, test. Il ne faut pas que ce soit
just here. Look, you can have a seat, please. Okay, so now it's time to start. So Pierre Ferrer, the jury members, give me the opportunity to be the president of the jury, so I accepted, of course. So I will introduce the jury member. So first we have Ramesh Arjani, which is a full professor from the University of Minnesota here. The second reviewer is Antoine Frappé, associate professor from Junia in Lille, just here. Yeah, we welcome Doug Smith, which is an engineer in Austin, Texas. And we have online Daniela Dragomirescu, which is a full professor in LAS CNRS. And she follows the link on YouTube. We have also invited Didier Belot, which is an engineer in ST Microelectronics. We have invited also Andrea Catlin, but she's not able to participate, but she sent me questions for you. And then we welcome also the advisors of your thesis, donc Hervé Lapuyade, associate professor in the University of Bordeaux, Yann Deval, full professor at Bordeaux INP in Thermalmeca, and François Rivet, also in full associate professor in Bordeaux INP and Thermalmeca. And myself, Nathalie Beltin, full professor at Thermalmeca also. So Pierre, you have roughly 45 minutes for your presentation, and just after we'll discuss about your work. So the floor is yours.
Thank you, Madam President. So, good morning, everyone. My name is Pierre Ferrer, and today I will present my work on a study of a radio frequency front-end based on Walsh sequences for the 5G standard and beyond. This PhD was supervised by Dr. François Rivet, Professor Yann Deval, and Dr. Hervé Lapuyade. Here is a quick outline of the work that will be presented today. So first, we're going to go through an introduction of the radio frequency front-end, or RFFE. Then we will move on to the Walsh transform for RF converter. Then high-level simulation for the Walsh transform will be discussed. Following, we will talk about the design of a Walsh-based converter. Then the measurements of this converter will be shown, and we will finish on the conclusion and perspective of this work. So, starting in the introduction of the radio frequency front end, in the 5G context. So the 5G is by definition a high volume, high data rate application. So as we can see here, one of the main applications that started not with 5G but with 4G, we have the connection between people, meaning text messages, video call, or audio call, which obviously are high data rate for the video calls. Then the 5G went beyond this area by connecting also objects throughout IoT or V2X applications. And one of the future applications for 5G and 6G are to connect intelligence, meaning connecting AI node, medical assistances, or do robotics or autonomous driving. So all of these applications are of very high data rate volume, and the demand in terms of data rate increases each year. And as we can see, during the 4 years of this PhD, the demand more than doubled. So obviously, the increase in demand leads to an energy consumption increase, which also leads to the need of higher energy efficient architecture, wider band architecture to deal with the data rate, and scalability, as it is a mass product-oriented project. So, a quick introduction on radio frequency front-end. Here we have a simplified classical architecture used in the base stations. So we can see that is made of the user data, which is sent to a converter, which has roughly of around hundreds of megahertz. Then this converter is upscaled to a higher frequency with a mixer and filtered to create and amplified to create a signal. So this type of architecture allows for carrier generation at RF frequency, but they also allow for carrier aggregation, meaning generating multiple carrier. Whether it can be contiguous carrier, meaning carrier that are side by side from each other, or non-contiguous carrier, meaning carrier that are apart from each other in the same band. However, this type of architecture can have difficulty in dealing with carrier aggregation with bands that are with different bands. So this is not easily accessible with a classical architecture, as these architectures are narrowband. However, it can still be accessed by using redundancy, meaning that multiple architectures in parallel are going to be used in order to address each frequency band required. However, this redundancy, while providing a wideband coverage, is not power efficient. So another approach to the standard architecture would be the direct approach. And as we can see, the direct RFFE is quite different from the standard RFFE, as in the standard RFFE, we have the baseband from the intermediate frequency that is performed by the converter, and then the mixer will move us to the RF frequency. In a direct architecture, we go directly from the baseband to the RF frequency. So obviously, the standard architecture reduces the constraint on the converters, which allows for higher linearity. However, it requires the need of extra components, such as mixers, which are narrowband. So this architecture have a very good linearity, but they are narrowband. On the other side, direct RFFE are simpler architecture, which is important for the scalability purpose of the 5G standard. But on the other side, they increase the constraint on the converter, as it must convert now at much higher frequency. However, this type of architecture are not yet wideband in itself. However, they are not narrowband either. So we can work with this. So two way of improving an RF converter will be throughout time interleaving and frequency interleaving. So the time interleaving concept consists in using multiple converter at different and which are different time slots are allocated to them, meaning that a multiplexer will address each of these converter and set it in the right time slot. Therefore, we can virtually increase the frequency of conversion without needing to create higher frequency converters. So this type of architecture improves the data rate. However, they increase the consumption as converters need to be set in parallel. The bandwidth in itself is not necessarily increased, this kind of architecture. And this architecture are also mismatch sensitive due to any mismatch occurring in the time slot will result in overlapping between the converters and increasing nonlinearities. However, this kind of architecture is not so complex, as we can use already designed converters, and only a multiplexer needs to be added. Frequency interleaving, on the other side, use the same principle. However, now the converters will not have a time slot allocated, but a frequency slot. So the interest of this is obviously the data rate can be improved since we have a wider bandwidth. The consumption, we will see later, is not necessarily as much improved, and the bandwidth is greatly improved. However, this architecture is still very sensitive to mismatch, and the complexity is even higher, due to the reason that frequency interleaved architecture require a dedicated architecture to be power efficient. So while they have a 1-bit capability, they are much more complex to design. So we will now move on to the Walsh transforms for RF converters. So first, here is a representation of the same sine wave at 15 Hertz. So we have here a time domain representation on the left and a frequency domain representation on the right. And we can clearly see that for the same information, we have different number of data quantity that are required to transmit the same information. In the Fourier transform, or frequency transform that we can see here, the data is much more compact than in the time domain. So obviously for converters, the more data we have, the more conversion we will do, the more power we will consume. So frequency architecture seems to have a very good interest when it comes to power consumption. So now we move on to the frequency transform. We all know Joseph Fourier, which tells us that any signal, at least any RF signal, can be a sum of sine waves. This is the Fourier transform. However, there is another transform, which is the Walsh transform, which tells us that any signal can be a sum of square waves. This is the Walsh transform. So we can see that there are differences between these two architectures. So for implementation, we need to understand which one is has the more advantageous for circuit integration. So when it comes to the Fourier transform, one of the main downsides is that we need to generate sine waves. And sine waves can be generated using VCOs or alternative architecture using passive components such as inductors, which can be difficult to scale. On the other side, the Walsh transform is based on binary sequences, and these binary sequences can be generated using logic gates, which are much more scalable, power efficient, and of a lower complexity to implement. So the Walsh transform seems to be the best candidate for integration. So here we have a comparison of both of these transforms with some parameters. So the first one, obviously, is the basis. The Fourier transform is a sinusoidal-based transform, where the Walsh transform uses piecewise constant signals. The periodicity is slightly advantaged for the Fourier transform, as all of the Fourier sequence are symmetrical. While the Walsh sequences have a periodicity, the periodicity is for a binary sequence. So it requires more steps to generate. The domain, however, is much more difficult for the Fourier transform, as these signals are sinusoidal, they are complex, while the piecewise constant signals are real. The sparsity, which means how much coefficient we need to recreate a signal, is at first better interesting for the Fourier transform, as singletons can be generated easily in Fourier. However, when it comes to highly modulated signal, the number of harmonics will rise and create a balance between the generation of sine wave versus the generation of square waves. The frequency source, as said earlier, is based on AC oscillators for Fourier, and the Walsh frequency can be performed with only a single source, which can be either sinusoidal or square. So it simplified this approach. When it comes to the operation, the Walsh transform also have an advantage. So while it uses multiplication in the mathematical equations, the binary nature of the Walsh sequence allow to perform this operation much easier, while the Fourier transform still requires multiplications and additions. So now we will move on to the principle of the Walsh transform and see a bit more in depth how it works. We're going to start with an example with a Walsh order of 2, meaning that we're going to have 2 power 2 sequences, so 4 sequences. So here are the first 4 Walsh sequences. These are constant sequences that can be generated using the Rademacher functions. So these are square sequences. And then we will calculate the Walsh coefficient on the data. And each of these coefficients will be multiplied by its corresponding sequence. And all of these weighted sequence will be summed to generate any signal. So this is the principle of Walsh. Sequences plus coefficient leads to the generation of a signal. We can see here that we have some specific sequences. First of all, the first sequence, which is the Walsh 0, is just a constant level, and it represents the DC level of the output signal. Then we have the first non-constant signal, Walsh 1, which frequency is at the refresh rate of the coefficients calculation. And then we have the last sequence, which is the Walsh sequence. And this frequency of this sequence is the limiting factor for the highest frequency that we can reconstruct. We can observe that all the sequences that are a multiple of 2 power n minus 1, so Walsh 1 and Walsh 3 in this case, are just square sequence with a duty cycle of 50% and an increasing frequency. These sequences are called primary sequences, and then can be used as they can generate all of the other sequences. So now we move on to the high-level simulation of the Walsh basis. And first, we're going to start with the targeted performance. So the goal of this project is to generate an RF DAX at the FR1 band, meaning the 0 to 6 gigahertz bandwidth. And as we can see with the state-of-the-art of RF converters around this frequency, is that we can see a floor limit at around 1 picojoule per byte, as very few work can get throughout this limit. So this is our target. We are looking to go under the 1 picojoule per byte efficiency. So the goal is to generate a wideband architecture in the 5G standard in the sub-6 gigahertz bandwidth with a sub-picojoule per byte efficiency. So the 5G standard tells us that to meet the specification, we need to have an ACLR above 44.2 dBc and an EVM under 8% for 64 QAM modulation. Our additional target of having an efficiency of under 1 picojoule per byte is also added, which leads us with parameter to define. So in the Walsh transform, there is 3 main parameters. The Walsh frequency, meaning the highest frequency we want to reconstruct, which is fixed by the project. The Walsh order, so the number of sequences we're going to use, and the quantization, meaning the number of bits we're going to use to quantify the coefficients. So high-level simulations are necessary in order to dimension these missing parameters. So first, we're going to start with the Walsh order. And how do we choose this Walsh order? So as the Walsh frequency is already fixed, the only thing that the Walsh order affects in your use case is the frequency at which we calculate the coefficient. So we can see here for a same signal with different Walsh order that a smaller Walsh order leads to having more slots to reconstruct. So technically, we are calculating coefficient at a faster rate at a smaller order. So the first thought that we can have is that we can say, well, let's take the highest order possible so that we calculate the coefficient at the slower speed as possible, so there is less constraint on the converter. However, as we can see, the number of sequences that needs to be generated is increases with the Walsh order. So with a Walsh order of 6, we already have 64 sequences. And obviously, while we reduce the constraint on the converter, the need of generating these sequences and synchronizing them improves the complexity. So there is clearly a trade-off between complexity and calculation speed. In order to settle this trade-off, we can look at the specification of the technology that we're going to use. So here is the datasheet of a memory that will feed our coefficient. And we can see that the access time is at around 440 megahertz. And for an F-Walsh of 8 gigahertz, this makes the closest highest Walsh order of 6, leading to an F-refresh of 250 megahertz. So we have our Walsh order. Now we need to figure out the quantization level. The first parameter that we're going to look is the data integrity that we will quantify with the error vector magnitude, EVM. We can see that the quantization level reduce the EVM, which is good in our use case, and that we also have some local minima at certain frequency. This local minima occurs at frequency that are multiple of the refresh frequency. So if we want to address the 5G standard, we need to have an EVM of less than 9%. And we can see that to achieve this, we need to have a quantization of at least 6 bits. So the quantization of 6 bits is the minimum for data linearity, for data integrity performances. But there is another parameter to look at, is the ACLR or the SFDR. So the SFDR is presented here. We can see that for the same behavior occurs is that we have these local maxima in performances that occur at some frequency, and that we can achieve an SFDR of around 40 dB for quantization above 8 bits. When it comes to ACLR, we can see that we have a bit less variations, but still, if we want to meet the 5G standard, we need to have a quantization of at least 8 bits. So this concludes to the performance that we need to have, is that 8 bits is the minimum for linearity performance. So it's the minimum that we can do to meet the 5G standard. So we can now move on to the design of the Walsh architecture. So all the chip presented has been designed in 28 nanometer FD-SOI from ST Microelectronics. So the advantage of this technology is first, it has many metal layers for the routing. It has 9 metal layers, which is very interesting for digital-based application, as it very simplifies the routing. Another interesting characteristic of the FD-SOI is its backgate control. So we can bias the body of the transistor to change the threshold voltage of the transistor. So this means that it can have many effects on the circuit, but for digital application, one of the main ones is that we can change the logic gates delay, which is very interesting in our use case, as we are going to need to generate many sequences, which are just digital buses, and the synchronization of these buses is important. So these features allow us to add a more fine-tuning to the circuit. So for both of these reasons, the 28 nanometer FD-SOI is well suited for our application. So we have here the architecture which is presented here, and it is separated into 3 main parts. First, we have the sequence generation, meaning the generation of the Walsh sequences, which are first separated in the frequency divider block, which will generate those primary sequences we saw earlier, meaning the sequences that are just square sequences with a duty cycle of 50%. And all of these primary sequences, as we have an order of 6, we need to generate 6. All these primary sequences generate after, by combination, all of the others. Then we have the coefficient generation. For this first tape out, the coefficient generation will not be performed on the chip, and it will be done off chip and then stored into a memory. And then the final block of the architecture, which is the Walsh coefficient and sequences combiner, which will multiply each coefficient with its corresponding sequence and sum all of these sequences. So first, we're going to go with the sequence generator. So the first sequence that we need to generate are the primary sequence, the 6 primary sequences, and we've decided to generate them using frequency divider based on the latches. The reason we've used this is that it allows to do a compact layout while keeping power consumption low. The latches used for this application are TSPC-based logic latches, and these latches advantages versus standard latches is that they can perform at high frequency, since we are starting at 8 gigahertz. However, this kind of latches cannot store data, so they cannot be used at lower frequency for data storing. So here is the post-simulation result of this block. We can see that we have the generation of the 6 sequences, with the frequency being doubled each time that we increase the Walsh order. We have a slew rate of around 5%, 6 picoseconds, which is standard for this technology, with a power consumption of around 1 milliwatts, and an area which is quite small, around the 4 micrometers square. So the secondary sequences can now be generated. The generation of the secondary sequences is presented in this architecture. So the generation, as I said earlier, uses the primary sequences. So first, we generate the 8 first Walsh sequences, which are easy to generate with the first few primary sequences. So we do it in one block to increase the compactness of the circuit. And once of these 8 first sequences are generated, we generate the next stage by multiplying the current stage sequences with the next stage primary sequence, and the multiplication that is performed using XOR gates allows the generation of the next stage of the Walsh sequence. Then, between each stage, D-latches are added in order to synchronize each of the sequences with each other, which is very important for the linearity. So the latches used for the syncing are also TSPC latches, as we are still at high frequency. And the sequence synchronization is a critical aspect of the Walsh reconstruction. So this synchronization is really important. However, as we can see, the last stage do not use latches for synchronization. And the reason is that the main clock and the last Walsh sequence are too close in frequency to each other. Therefore, the latch cannot latch with this sequence. So we use a buffer with body bias control. So the advantage of buffer is it allows for adjustable delay. We can fine-tune the delay after the fabrication. However, as these buffers are sensitive to the manufacturing process, we need to perform a manual operation to sync the sequence once the chip will be fabricated. So we have here the post-layout simulation of this buffer, and we can see that for different body bias, we can achieve a span of around 24 picoseconds of range. And we're going to see, so in the next simulation, if this is enough. So we have here the secondary sequences that are being generated. We have here the layout, which is compact thanks to the only use of logic gates. The slew rate is similar to the previous block with around 6 picoseconds. And Monte Carlo simulation have been performed in order to quantify the shift between the last stage and the previous stage. And we can see that we have a maximum span of around 5 picoseconds, which is well within our 24 picosecond range of our buffer based on the body bias. Therefore, the backgate control allows for sequence synchronization. Now we can move on to the coefficient generator. So the coefficient generator for this first tape out is not based on a full memory, but will be based on an SPI. So we will not be able to change dynamically the coefficient. However, this is enough for a proof of concept. A 512-bit SPI allows for single tone generation at frequency multiple of the refresh frequency. So the process that we're going to use is that the coefficient will be pre-computed on MATLAB. Then they will be stored at an FPGA that will load the data into the chip synchronously. However, we still need to design a 512-bit SPI. So this SPI is presented here, and it is based on smaller SPI, which are 32-bit SPI. The reason we use smaller SPI is that these SPI have already been tried and tested in previous runs. So we put SPI in parallel with a multiplexer to achieve the 512 bits necessary. These SPI are based on standard D-latch, so not anymore TSPC latches. And all the components used are standard ST library components for this application, which are enough as we are not going to write in the SPI at high frequency. So we have the clock tree, and which is present for the clock distribution of the SPI, and we also have between the stage buffer so that the data do not arrive before the clock. The area of this SPI is of 0.072 millimeters square. We can now move on to the last block, which is the coefficient and sequence combiner. So the coefficient sequence combiner is the main block of the architecture as it has the most constraints. So it is based on current steering DAC, so modified current steering DAC. As we can see that we have added this switching. So the architecture is a 7-bit architecture with 3-bit binary and 4-bit thermometer. And the reason we use this is that it's a good compromise between the compactness of the binary coding and the linearity of the thermometer coding. So we use this trade-off, which is a standard trade-off for this kind of number of bytes. So we are performing the sequence combination at 8 gigahertz. The last bit, which is the sign bit, is dealt via sequence inversion, as in the Walsh basis, an inversion of sequence is similar to a change of sign. So it reduces the constraint on the converter. We can zoom out on the unary element here, and we can see that it's a standard differential pair with a current source and a current mirror, to which we have added some extra features. The first one are the 2 switches that are present. So these switches allow to switch on and off the current source, as the conversion in a standard current steering DAC occurs at the switching transistor. Here, the sequence will come. So the sequence weighting will be performed by switching on and off the differential pair. So we use 2 switches. The first one near the current mirror in order to shut off any current consumption during the off phases, so that this block do not consume any energy when it's shut off. And the second one is closer to the current source transistor to be able to have faster off switching. In order to improve the linearity of this block, we have added cascade transistors and neutralizing capacitor to reduce the charge injection effect, which is very important at this frequency, especially with square-based signal. We have here the post-layout simulation of this unitary element. So we have a sequence at 8 gigahertz, which is switch off, and we can see that the commutation lasts 250 picoseconds, which represents 6.5% of the coefficient period, and not the Walsh sequence period. So we can now move on to the sign bit computation. So as I said earlier, in the Walsh basis, a negative sequence is equivalent to an inverted one. So we control the sign by inverting or not the sequence with switching logic and inverters. And then we need to generate complementary signal for the dereferential pair. So we do that by a combination of inverters and pass gate. And we also use set reset latches to ensure proper symmetry of the complementary signals. So we have here the post-layout simulation of this block. We can see that the sign occurs, the change sign occurs properly, and that the signal are properly complementary. So now we can move on to the post-layout simulation of the full converter. So the first simulation we have performed is simulation all across the levels that are possible to recreate with this converter. So we can see that we have a good slope linearity overall of 0.04%. However, if we zoom out in the middle, which is the transition between the 6 LSB and the MSB, which is the toughest transition to do, we can see that we have a DNL integrated over the coefficient duration and not the Walsh sequence frequency of 0.03 LSB, which is satisfactory for our use case. So we have here the layout of this block. We can see that we have separated the current mirror resistor of the transistor to ensure good capacity. So obviously, these lines, which are not necessarily of the same size, changes the resistivity of the current memory. However, the transistors are in a better position of being closer to other transistors rather than spaced with resistors. So we have here the post-layout simulation of the final architecture. We can see that we have performed simulation on single-tone and two-tone signal. However, the idea of this project was to do wideband signal generation. So here we have a three-tone signal all across the bandwidth. So we can observe that we first have an SFDR of around 11 dB with mismatches in amplitude. These mismatches can be resumed using calibration. So the calibration is performed by mapping the nonlinearity in amplitude of the architecture. So we generate a signal which is just multiple sine waves spaced with 100 megahertz all across the bandwidth. And with this, we map the amplitude that we expect, the difference in amplitude between the expected and the measured, and the simulated more. And then we applied an inverse filter on the coefficient so that we can compensate this effect. The calibration is shown here, and we can see that we really improve the SFDR as well as the amplitude mismatch as we go from an amplitude mismatch of 3.56 dB to 0.17 dB, while having an output power of around minus 6 dBm. So we have here an overview of the results. So the chip is presented here. We have a core area size without the SPI of 0.140 millimeters square, which is quite small, an SFDR of 15 dB, an instantaneous bandwidth that has been validated in simulation of 4 gigahertz, which is the main interest of this architecture, and a power consumption which is quite low at 44 milliwatts. The power consumption is detailed in this tab, and we can clearly see that the main contributor for power consumption is the buffer interconnection, meaning the buffer between the sequences and the DACs. So these buffers are always on, technically, so they obviously consume a lot of energy as the signal is at high frequency. So there is room for improvement for these buffers, as the sequence generation and the combination is not so high compared to this, which consumption results in an efficiency of 0.34 picojoule per byte, which is quite low. We can now move on to the measurement of the circuit. So this circuit was fabricated with the ST process and packaged in 48 pins package. We have here a photograph of the chip. We can clearly see the different elements of the architecture. And here is the test setup that has been used to perform the measurement. So the test setup uses test PCB, as we have packaged the chip that we put into sockets. So we can change the chip. We have an FPGA that will allow to store the coefficient on the chip, a computer for coefficient calculation, signal generator for the main clock generation, power supply, and a high data rate oscilloscope. So we need to have a multiple input oscilloscope as we are using differential signal directly. So here are the first measurement. So first, Walsh sequences has been measured. So we have tested one of the first sequence, Walsh 1, at an f-Walsh of 1 gigahertz and an f-Walsh of 4 gigahertz. We can see that the reconstruction is properly done. And we have also measured a more complex sequence, which is Walsh 18. And we can see that the comparison with the ideal sequence fits. So all of these measurements are measured at the output of the chip and not inside the chip. So it's really the RF output of the chip. It's not a short from the sequence generation. So, which means that this first measurement validates the sequence reconstruction. but it also validates the DAX functioning. We can see the power consumption at different frequency. So we can see that for gigahertz, we are near of 44 megawatts. And the power consumption is coherent with simulation. So this measurement validates the second generation and the combination. Next, we have signal generation. So as a disclaimer, the measurements are still ongoing, as we are still having issue with the SPI we've used. So we are still debugging the SPI, so the measurement are still not finite measurements. However, we have still managed to generate more complex signal. So with an F-Walsh of 1 gigahertz, we have managed to perform a simulation of a sine wave at 0.5 gigahertz. So we have here the time domain and the frequency domain representation of this signal. And we have a power consumption in that use case of 36.6 milliwatt and an SFDR of around 15 dB. So these results are coherent with the simulation, and they also validate the functionality of combination between multiple sequences. However, measurements are still ongoing, so measurements are still ongoing. So we can move on to the conclusion and perspectives of this work. So we have here a comparison with the state of the art. The parameters compared here are post-layout simulation parameters, as the measurements are not finished yet. So obviously, as we can see, the power consumption will increase. So if we compare ourselves with the state of the art, we can see that one of the first areas we shine is the core area of the chip, which is the smallest of the state of the art at 0.140 millimeters squared. Another big performance that we have is our instantaneous bandwidth, meaning the capability of sending multiple carriers all across the bandwidth. And we can see that for RF DACs, most of the state-of-the-art do not even specify this metric, as most of them use single-tone signal for DAC measurement. The other one is obviously the consumption, which is quite low, which leads to a power efficiency under the picojoule per byte. However, we can clearly see that the linearity is one of the worst of the state-of-the-art, and that there is room for, and that while we have good consumption, bandwidth, and area, linearity still needs to be improved. So the conclusion of this work. So the Walsh transform was studied, and its digital approach has been shown to be well suited for CMOS integration due to it reducing the amount of required conversion. The wideband characteristic of the Walsh transform has been shown in high-level simulation and post-layout simulation. And the first design of this architecture has been done at 4 gigahertz of instantaneous bandwidth with a power efficient below the 1 picojoule per byte efficiency. Finally, the circuits have been fabricated and the functionality of the circuits had been validated, while the performance still need to be measured. So here are some quick perspectives of this work, as there are many. The first one is obviously to implement a memory in the chip rather than an SPI, which will allow to validate the wideband functionality of the architecture and to generate more complex signals. The second aspect is to improve the linearity of this architecture. So one way of doing it could be throughout predistortion, digital predistortion of this architecture. Here we have the AM behavior of this architecture, and we can see that it's not quite similar to power amplifiers. As while we still have an overall linearity, we have huge memory effect with a normal distribution. So standard approach are not the most optimal. We need to have a statistical approach to deal with this memory effect. Another thing that could be done on this architecture will be to have more of a path-based approach, meaning that the thing we do with this first tape out is that we generate all the sequences with the most optimal and compact way, and then we multiply them. However, the last sequences are dependent of the first sequences. So we cannot shut off any path. All the sequences are always on. So this improves the power consumption. And doing a path-based approach could improve the power consumption, but it also could improve the layout, reduce the layout complexity. While it would technically improve the layout area, the complexity of layouting will be lesser, which is quite good, as at 8 gigahertz, we need to lay out by hand the Walsh sequences, which is time-consuming. A last aspect of the perspective of this world could be the coefficients tuning, meaning changing the coefficient to fit more with the architecture. The first one would be to improve the energy consumption by coefficient truncation, meaning removing some low-impact coefficient to reduce the coefficient of the overall architecture. However, as we saw, the main downside of this architecture is more the linearity. So we can do the opposite effect of the truncation, which is deterring, meaning that we can add a noise floor to the coefficient to dilute the quantization noise and improve the linearity. However, it will improve the power consumption as well, as we are adding noise to the coefficient. So here is the list of the publications. We have had one journal in IEEE Access, 2 international conferences in AVIC and ICECS, and 4 national conferences. So thank you for your attention, and if you have any questions.
Excellent presentation, and your time is perfectly respected, so thank you also for that. So now the PhD defense is open for discussions with jury members, and we will begin with Professor Ramesh Anjali from the University of Minnesota.
Here, you focused on the DAC side of things.
Yes.
Even with this DAC, are you able to reuse a traditional receiver front end, or do you see some changes would be needed for traditional radio receiver?
Technically, for a receiver, we can use any kind of receiver. It doesn't change. As we are generating standard RF signal, they can be used with a standard receiver, which doesn't use the Walsh transform. However, for linearity perspective and error correction, obviously, if we have also a Walsh receiver, we can perform calculation directly in the Walsh basis that could be useful and that could help to correct any error or linearize better the architecture. So we could benefit for a Walsh receiver, however, it's not necessary.
Follow-on question. The overall architecture of the DAC typically has a low-pass filter.
Yes.
Most DACs. In your case, what is that and trade-offs of that?
So, as we saw, we do not use any filter in this architecture, and obviously it has some downsides. The first one being that while we compare ourselves with the ACLR, which is the specification provided by the ETSI specification, technically our ACFDR can also be considered of ACLR, as we are not filtering. So this first approach was done without any filtering to just showcase the functionality, and adding additional filtering would necessarily be, as we are a wideband structure, reconfigurable filter. So obviously it will add another layer of work to do. So the first approach was to do it without any filtering. Obviously, for high linearity performances, it is clear that filtering are going to be necessary for the noise that are away from the carrier, as the ACLR itself is quite good in itself compared to the FSFDR. So we do not use a filter. However, for wideband application, reconfigure a filter would be a good option.
So in terms of the reconfiguration, so you would probably do some kind of reconstruction filter, constant bandwidth. But you're saying reconfigurable, that would be, so depending on signal channels that you're using, you would reconfigure that, is that what you're thinking?
Yeah, I think it would be the more, it would be the most, it will be the approach that will lead to most application to be able to have a reconfigurable filter. However, if we have, let's say a transmitter is based for certain type of frequency, like 3 main frequency band, we could use standard filter for filtering. However, if you want to be able to use the band in its entirety, if we want to have the wideband capability, the reconfigurability, in my opinion, is necessary.
For the calibration that you ended up doing, so this calibration is done for amplitude only.
Yes.
Do you see a reason why you may or may not need to do phase calibration?
So this first calibration was done on amplitude, as when it comes to converters, the main parameter that is showcased usually is the linearity of the converters. So it's the first thing that is presented. So that's why we focused on this mainly. When it comes to phase offset, obviously for 64-core modulation, it's a really important thing to look at. What we've observed as in the simulation, it's really complicated to do proper modulated simulation, as the time is very long. And therefore, the only modulated simulation we have been able to do was to do few samples with a 16 QAM. So the simulation is hard to perform for phase calibration. That's why we've not focused on it the most. However, now that the circuit is fabricated, maybe it could be easier, as we do not have to wait this long. So phase calibration is obviously a big issue, and in my opinion, the way that we could improve it would be to fine-tune each sequence and each DAC to ensure the best synchronization. In my opinion, that's the way we would better fit. It would be to fine-tune the delay between each sequence and the delay between the DACs to be able to have the best synchronization, as synchronization will lead to good phase performances, or at least to reduce the phase offset.
Probably for the sequence generator, but there's a low, because you have a maximum bandwidth, right, which is falling off. If you think about multiple poles, it's having amplitude and phase.
Yes, yes, obviously.
You'll have to do multiple, I think.
Yeah, yes. But yeah, this has not been yet.
I was just.
No. It's a very good question.
So I don't know Walsh well, Walsh transform. So in Fourier transform, you have Fourier transform and then inverse Fourier transform.
Yes.
And sometimes when you're trying to do certain kinds of signal processing, it's sometimes better to do in the frequency domain, sometimes it's better to do in the time domain.
Yes.
Do you have a sense of what Walsh will give you or what trade-offs are available to you?
Yeah, so obviously, as we are doing inverse operation, we can technically have non-convergence when doing this inverting, which can be an issue in all types of frequency architecture. Technically, while the computation of the receiver and the Walsh computation is less my main thing, it's more the next PhD that will be tomorrow. So maybe you will explain it better than me, but we have observed some improvement in the convergence with the Walsh transform rather than in other typical use transform. So technically, if we have a faster convergence, it could potentially reduce the issue that we have with inverting. However, it's not something that I've studied in depth. So maybe Maxime tomorrow will be better suited for this answer.
I think that's my last question. In the power consumption, the power consumption numbers that you shared with us is for not the sequence generation, but for just the Walsh. What all do you have calculated in your power consumption number of 0.34 gigajoules per bit?
So the way we've done this operation is by doing it the way not time interleaved, but interleaved architecture perform this calculation. As technically, as we are not in the same basis, maybe a quantization in the Walsh basis is not necessarily completely similar to a quantization in the time basis. So this number is here to compare ourselves. The way we've done it is that as we have many converters that are all working together, and they each have a data rate of 250 megahertz, we've used this matrix, timed the parallelizations to get to the efficiency. So we have not done some equivalent between the different transforms. We have taken it a bit like the first approach. We have X converter at X frequencies that are in parallel. Therefore, we have X gigasample per second. However, if we would do a proper, maybe we should do like empirical or measurement of this data rate to have the proper data rate that we can really achieve and compare us this way with the efficiency. That would be the most cleaner approach. But as no one does that in their comparison, we've decided to compare us the same way everyone does. So obviously, it's one of the main difficulty of this structure is that which are our way of comparing each other. RF DACT, radio frequency front end. Neither of them is fair for either of us. So if we compare ourselves to our RF front end, obviously there is much more linearity, filtering. It's not fair to compare ourselves to them. And with DACs, RF DACs, it's not fair as well as we do not have the same bandwidth. So we are not comparing the same things. So it's difficult. We have to use the same method. So we have at least coherent metrics, but yes, it's one of the difficulty of this work is to how do we compare ourselves to the others without being completely optimal.
Last question, sorry. In terms of your linearity was not good.
No.
What do you think are the causes for that? What do you think are the causes?
So as we saw in the simulation, we can achieve higher linearity. And the main cause of non-linearity, by far, is the mismatch and the non-symmetry in the signal. So the first one, the mismatch, obviously, the sequence, there is the jitter, there is the time, the rise time, the fall time, everything. So it reduces the performance greatly. However, the signal are by nature, while we use complementary signal, they are not symmetrical in any way, as the rising of the transistor and the falling edge of the transistor is not even symmetrical. So our differential is not even properly differential, by say, so it adds another layer of error. And the main contributor of error throughout is also the layout. The layout is really, it's a really big circuit to do. And everything has to be done by hand as we are performing at high frequency. So the path of each sequence are not equivalent. Even in sub-paths, they are not equivalent. It's really hard and really tough to generate 64 sequences and address them properly. And the last thing that really, really decreased the performances, as I saw in the post-layout simulation, is the buffers. So the buffers between the sequences and the DACs are really tough to do due to the fact that the Walsh sequences, while we've tried to do it as small as possible, they are so small that compared to the DACs, like the length of the path is much greater than of each pass is much greater than the length of the whole sequence generator. So it also adds another layer of mismatch. So it greatly decreases the performances. So that's why I'm more looking toward the path-based approach, so we can have more consistent delay between each lines. But and the last thing that deal with linearity is the way that we've done current mirror, as we needed to have a high scalability with the current mirror. Just a single resistor is not enough for proper linearization, as it's even worse that when we increase the unary element to deal with the every bit, the relation between the resistor and the current is not necessarily very linear, as the doubling in sizing of the transistor doesn't necessarily result in the doubling of the bias current necessary. So, which makes that every resistor is not properly linear throughout each other. So when the process variation occurs, there is mismatch that is put intrinsically. So even if the resistor have the same mismatch, the result in current will not be the same. So to complete the circuit, is very huge and has lots of elements. So we have to do choice to do things on time and by my own. So obviously, this leads to choice that are not optimal in terms of performances at all. So.
Thank you, Ramesh. So now we give the floor to Antoine Frappé, associate professor in Julien.
Thank you very much for this nice presentation.
Thank you.
Yeah, it gives a little more insights and it answers some of my questions.
Yeah, I've tried.
A good point. One of the first questions I had reading the manuscript was like, why you get interested in the Walsh transform and how to compare to a Fourier transform. So you answered this like in one of the slides at the beginning of the presentation. So I think for that it was kind of like an understanding for me, and so you gave a lot of arguments towards the Walsh transform. But I'm still curious on how it compares in terms of performance. Is there an equivalence, like if you use the same number of coefficients in Walsh transform and Fourier transform fundamentally, it's equivalent? Is there any chance the Walsh transform is also gets some advantages?
Of course, if we take the differences between the transform mathematically, for typical RF signal and let's say lower modulation, I will not be surprised that the Fourier transform could outperform theoretically the Walsh transform, as we use square-based signal and the receiver is expecting sine waves type signal. So obviously the generation and the co-integration with other architecture will probably benefit the Fourier transform if we take it mathematically. However, when we start to look at highly modulated signal with high wideband, the number of harmonics is so high that we've not the metrics to compare to this. It will be interesting, obviously. However, when the number of harmonics increasing so much, the difference between the two is more balanced. So I would say that for simpler signal, Fourier seems to be a better choice. And without even considering the fact that it's something that everyone knows, so it also adds to the complexity. But for arbitrary number of harmonics to reconstruct, probably that both of the transform have some equivalence. And maybe even Walsh with the calculation conversions can be performed better on the computer.
Okay, interesting. So as a follow-up question to Ramesh, final question. You indicated very early in the manuscript that the structure is very sensitive to the phase between paths and also to the shape between paths. So all your simulations, at the beginning, do not take into account the mismatch. So when you get your
No.
40 dB
No.
SFTR, you have no mismatch.
No. It's not technical mismatch.
Yeah. And then in terms of methodology, you design your chip, and then
Yes.
at the end you say, oh, I don't have 40, I have something like 15.
Yeah.
Right? Okay. So in terms of methodology, it would have been beneficial to estimate what are the specifications in terms of mismatch.
Mm.
And
And compare with.
so my follow-up question is like, where is this drop coming from exactly? Do you have any did you like reduce, simulate your
So
it was like MATLAB
yes.
bench? Did you reduce, simulate to actually find whether it is the phase alignment, jitter?
So
whatever?
it's every part of the architecture like increases the mismatches, but the main differences that I've seen were with the schematic simulation and the post layout simulation. This drop, like we lost almost, I mean not 10, but around 8 dB of linearity, which is really high. And one of the things that occurred was especially with the TSPC latches that we used. These latches have a downside that was not shown on the schematic, was that they kind of chip off the duty cycle. So if we use a TSPC latch, it will reduce the duty cycle, so the upside will last longer than the downside, and it's always the same. It's not one time the up level is high and one time it's the low level which is extended. It's always the same. So it's a problem because it's cumulative. And with the XOR gate, what can happen is that if we have mismatch that is caused plus slew rate that is changed or duty cycle that is changed, we can have this extra multiplication that will occur on technically a symbol that does not exist. So the D latches has been quite a huge deal because we've observed huge differences between the schematic and the post layout. And the most vicious part is that these differences could only be observed once the full block was designed, because that's where the linearity occurs. And even, I mean, we could observe it.
For example, like the energy of one bit or the slope or the phase, as a model in MATLAB.
Yes.
Pure.
Yes.
And then
yes, of course, we could have seen it, but we had already taken margin when it comes, because the main reason that this duty cycle is degraded by the D latches is due to the driving. When the driving is more difficult, it occurs even more. So if the signal comes sharp, there is usually very low duty cycle changes. However, as soon as we start to have like capacitive effect that occur, it increases. And we've had taken margins in terms of driving of order of 2 when it comes to the driving, and this effect was still like really present. And it was hard to spot as for the smaller order, as we have only 2 latches, we do not spot this huge difference in duty cycle. However, when it goes to 6, 7, 8 latches, that's where we start to have 1%, half than a percent, maybe 2%. But this is enough at this frequency with the slew rate to really create a big difference. So these latches, and I would say maybe for improvement, a more in-depth study of the latches, because there are many topologies that are available in TSPC. This one were chosen for having the best compromise in terms of duty cycle. However, there is many architecture, and like it could be explored in different ways.
So I'm more like on the circuit side. So I'm talking about latches.
Yeah,
so
yeah.
Let's dive directly into this part. So I think that's slide 25. Yes, I think you can do the match. Yeah. Okay, yeah, so don't really understand this structure. Like it's a very frequency divider. But how can it work with latches? Like since the latch is transparent, it's transparent on the high level of the clock. Right? So in my understanding, when you have a high level on the latch like this one, like this Q bar feedback on D would create an oscillator. So why should it oscillate?
It's a tough question. So this structure is it's quite an advanced structure and is not a standard structure, as the main things with this structure are these that we have floating points in these latches. So it uses the intrinsic capacitive effect of the transistor to operate. So it really has a high level of complexity to it. And to be completely honest, I've not studied in real depth all the effects and the stability issue with the latch.
Yeah, my question was more fundamental on the divider. You can use a divider like this one, that is flip-flop, but if you use a latch, I don't understand how this can work. So
I mean,
I wonder at first, like in the manuscript, it was
yeah, it's maybe it's
okay, maybe the latch term.
no, it's a yeah, yes,
But
it's
your structure is really a latch. Your TSPC latch, it's a latch. That means it's transparent when you have like clock at high. D goes directly to and give Q to R. So I really wonder what's the trick.
So I think it can still be considered a flip-flop because this first stage alone is the latching itself, I mean maybe it's like a correct an incorrect way of formulating, but I think it can be considered as a flip-flop, as it has all the same. But
I don't think so. It's not a flip-flop because on the high level of clock, you have like 4 inverters, right?
Yes, yeah, fourth stage of inverting.
It's a real latch.
Yeah.
Yeah. So like something I couldn't really understand. So maybe there's some flip-flop. I mean, if your simulation is running and you really get some division. I don't know if
yeah, we've measured the square as well. So.
Your simulation, or was there something that I missed somewhere? Okay. On this specific, so you mentioned there is a lot of different structures possible for this kind of latch. So why did you select specifically this one? As, this one is not a full swing latch, so the point is like after the first clock inverters, you don't have the full swing. There are other TSPC latches with full swings.
Yes, there is some smaller latches. So the TSPC latches can be performed with different structure, and usually the smaller latches have, I believe, have this full swing. However, the choice of the latches was maybe a bit forward. Is that we've tried most of the one used in the literature, and we've observed that for high frequency, despite them being much complex and much bigger than the smaller alternative for TSPC, this one had the better, not only the better not linearity, but the better performances, but it also had the best driving of other structure.
Why is that?
I think it has to do that we have more stage of inverters than in more regular architecture. So we do not directly go from one stage with 3 to 2. We go first with 2 inverters. I believe it improves the driving capability because.
So the driving capability is just like the last stage, right?
From my observation with this technology, it's usually not only the last stage, and it's the sum of all the previous stage. So if we take a really bad signal and we put it in front of a buffer and a slightly better one, at the output we will not have the same driving capability. It's Maybe it's due to the size that we use minimum size transistor, so that they do not have and we have at high frequencies, so the gain is not super high compared to the frequency. But from my observation, buffers in series improved to a certain point, obviously, the driving capability. So maybe that's more effect due to the frequency and the size of the transistor itself.
Let's talk about this structure. During my PhD thesis, 15 years ago, I kind of used the exact, not the same structure, but the same kind of flow. There was one main disadvantage, is that this one is dynamic, right? So if you don't activate it
Yes.
very often, and I think you described that in the
Yes.
then the level drops, and especially when you use it with a feedback, then it starts to oscillate by itself.
Yes.
So it has a limit on the frequency, like a lower limit.
Yeah, cannot be used for data storing either.
Have you evaluated this?
Yes.
This structure?
Yes, we've evaluated this. Obviously there is not so much like for this specific structure. The equations are not necessarily here. However, and it also depends on the transistors themselves and the frequency also. So I've studied personally this latch up to frequency, and in simulation, we've observed that this latch could actually go quite low in terms of frequency, at around hundreds of kilohertz. It was working fine. However, in measurement that we've seen with Maxandre circuits, which use it at smaller frequency, we've seen that there were trouble even at the megahertz frequency already. So we have a huge disparity with the simulation on that point. So probably that a more in-depth study would be done, but usually around the megahertz for this technology and this size of transistor is where we're at in terms of lower frequency. So as we are at 250, we are from it, but still we've had a huge bump in the simulation and the measurement. So I
felt the chip due to this TSPC flow.
Yeah.
So when I've seen this paper, I said, wow, 250 megahertz as an output, this one is even more.
Yeah.
So I felt the chip because it was pretty much the same. So I felt it because the other part of the chip was not operating at 8 gigahertz because for other reasons, like extra heuristic distances. But it would have worked definitely nice at probably like 4, something like that. You can see. But then this guy wouldn't go down, and I can only operate it at the high frequency.
Yes,
so
yes.
I was like, designing it for high frequency, and I did not think about test before. So that was my fear when I read the test. How would you test functionally at lower frequency?
Yes, it's clearly yes. This structure has been tested in different circuits. So we already had in this circuit that we designed in this technology. So we already had feedback on it. However, it's true that it had not been properly measured in order to really see the performance that we could put off. And what we saw with Maxandre results really showed us that, okay, 250, we were far away from any trouble. However, I think for next work, it should be considered heavily. Because especially if we have any issue with performance and we need to drop down the maximum frequency, there can be a problem, and it could really not allow the functionality, not even validate the functionality of a circuit just because we can't even go in low frequency. So
my next question relates to the synchronization. You have this body bias pin that you want to use to equalize delays.
Yes.
So effectively, you show the simulation when you have this 24 picosecond span that you can adjust on each of the paths, right? So I think that's a good idea because the chip is very sensitive to this phase.
Yes. So,
the path. But my question is, how would you do the synchronization phase, the calibration phase? So what is your strategy to actually measure or get like an indirect measure of the phase and the position, like the relative phase of each path, and how would you recognize for that?
Yes. So in simulation, obviously, it is easy to do, as as we can see all the signals at the same time, so we can perform. So one way of the thing that I have not described is that first, this buffer is biased at the middle point, so we can have both sides of the span. And in measurement, as I saw in measurement, it's a bit more tricky to do, as like by definition, like for measurement, it's as we have only two outputs with the chip, it's quite hard to plot two sequences at the same time to compare the phase offset. So the way we could do it is that we could use one of the clock reference and quantify the delay with this clock as a reference, and then perform different measurements as the clock is generated outside the circuit, and we can change the value of the coefficient without affecting it. So we can generate two sequences one at a time, quantify the delay between the main clock, and then apply a delay with the body bias control. Another way to do it would be to have more of a performance-based approach, is that we could generate a signal that we know will require the specific sequences, and fine-tune the body bias control. So when we have the best performance, that's where we're at. So one of the...
There's something like 64
no, we have not controlled all the 64 sequence, only the last stage. So we have the 32 last can be biased, because as I said in this slide, we cannot compensate the delay of the 32 of the last stage with delatch. So it's only the 32 last that can be, as a group, can be modulated in the previous stage. So obviously, a control of each sequence individually would be the best case, but we would need to have some sort of multiplexer with analog inputs, as the bias is not a digital one. So it's possible to implement.
So I didn't get that. Yeah. So you have a global...
Yeah, so the 32 last and the 32 before can be synchronized this way.
Okay, so you cannot calculate for any...
No, I cannot take one specific sequence and...
only like the whole sequence?
Yes, the group. The group. Yes.
Okay.
It could be implemented. In terms of complexity, it's just a matter of efficiency in doing it. But the reason we've done it is that because in the simulation of mismatch, this last stage mismatch is the one that brings the most nonlinearity when it comes to signal reconstruction.
You mentioned at some point that you have a computation time of your TAC of 200 picoseconds.
Yes.
50 picoseconds.
So you are...
And, you said, okay, that's cool, but 6% of the period, which period? The one of the refresh period?
Yes.
Yeah, so we said, okay, that's 6% of the refresh period, but that's more than the period of the Walsh period, the 8 years plan.
Yes.
At Walsh. So that's still an issue, right?
It adds nonlinearity as well. So this commutation, this commutation as well adds another layer, because we are integrating this commutation time over the overall coefficient. However, as it occurs at the refresh rate frequency, first of all, it will kind of attenuate a little bit the transition between every, so every transition won't be as smooth as it could be. And it will degrade the performances as well. So the 250 is kind of a worst case in that area, as it's the highest frequency with the switch off, which is the worst part. The switch on has better performances. So this is the worst case, but yeah, it degrades the performances as well. So being able to switch on and off this structure would greatly improve the performances. Or we could think of a way of not having to switch it on and off as well. So there are other
Did
applications.
you use any mismatch reduction techniques in your DAC? So from the layout, it doesn't seem.
Do I have a layer? I don't. I think we can see the whole layout, but I don't have a picture of the. So we have here the DAX, and the way the mismatch have been tried to be contained was through, first of all, the DAX are not put 1, 2, 3, 4, 5 until 64. They are placed depending on their frequency and depending on their spacing for the connection. So I've tried to have as much distance as possible that are equal just between the paths of each of this structure. However, as we can see, since we only have room on the top and the bottom, like we cannot do miracles. But this had been considered in the design, and especially for the highest frequency sequences that has the most difficulty. So we cannot zoom in on this picture, but the highest frequency are set at the edge of the generator. So they are the closer one to the buffers, and the delay has been set to match with each other. So this has been first done. When it comes to the DAX, so obviously for the mismatch, the transistor has been set as close as possible to each other, and all passive component has been sent a bit aside. And there are bridges also of dummy transistor between the stage to really make them being as one to the other.
That was the same environment.
Yes, they have the same environment, and the delay have been.
What is the resistor type? Because you use one resistor per unit cell.
Yes, so it's poly resistor types. So
Okay, so I mean you introduce like
variation.
you have the source by itself that you introduce mismatch.
Of course.
The resistor, since you choose to have like one reference resistor per unit cell, is also introduce extra mismatch.
Yes. However,
So why did you choose this structure with one single resistor per unit cell rather than like a reference current somewhere?
So there is two main reasons. The first one is obviously simplicity of implementation and scalability, as there is a whole architecture to do. So this is one of the first one that's been implemented. And when we say that we use one resistor, we of course we use one resistor, but it's separated in fingers that are smaller finger of the same size. So we have an array of finger, and we do not have one huge bar of each of the resistance of different thickness to change. So this is the first reason. And the second reason is that we need to be able to switch on and off this current mirror. And this really had the constraint on the current mirror of many topology. Like if we open the circuit, the switch back to on can introduce like spikes in the current call, and it can, while we have a very good stability and across different transistors, we can introduce a huge commutation problems. Where this structure, while being, of course, simple, probably too simple, doesn't have this much issue with commuting.
Still, because you're switching on and off.
Of course.
So you still have issue with commutation.
We have.
You see that in the time it
Yes.
takes to get back on.
We have.
So it's like 250 because. So what would you do to get rid of this commutation?
So there could be different approach for the current mirror. So maybe not doing as much like individual current, and maybe scaling them more according. So it won't reduce the commutation in itself, but at least it will reduce the mismatch. And for the commutation perspective, maybe extra, like I don't have like an idea right now, but the way of doing it by two transistors with only like the switching being occurred, like it's just switching, but we could improve also maybe something to help the start, to kickstart it a bit faster, to do pre-switching. So I don't have a topology in mind yet. However, there is yes, room for improvement definitely in this area.
So concerning circuit design, I have a last question. That was not addressed in the manuscript. I mean, one block is not addressed in the manuscript and not in the presentation.
Okay.
Is the clock input.
Yes.
So how do you get like 8 gigahertz to go in your chip?
Yes.
And
So the clock input, we can see it very, very tiny. It's here. I can't even point to it. So the reason it was not explained in detail, it should have been, is that I was not the designer of this input clock. It was done by someone else, and it was already used in different circuits. So it should have been put, but it's so that there is no originality to it. So it's just an inverter-based amplifier, which has quite good library, with a command-centered structure to ensure that we. So basically, it's just here to ensure that even if during this transmission line, even if we have an offset or a reduce in the center of the clock, it's set back center to 0. So it just inverter.
It's not common century.
No, it's not properly.
With the
Yeah.
wrist of that, right?
Yes.
And then it's the couple.
Yes.
Okay, makes sense.
So and it's
In the measurement, do you see any problems?
it worked.
8 gigahertz in your chip?
Yes. 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 Yes.
You
Yes.
showed measurements at 1 and 4 gigahertz.
Yes, and we can already see
And,
the.
get a chance to higher.
Yes, yes. So we went higher. However, with this current setup, we see huge problem with the clock, especially at higher frequency. So the issue that we have is that the clock is everywhere. The clock is everywhere. And
Did you match it like 50 ohm somewhere near your chip?
yes, yes, it's much 50 ohm on, I think, on the input.
So on the PCB or on the back?
Yes, on the PCB. We have some, but it's not it's like here it's high impedances. On the input we have some on the PCB the 50 ohm matching, but it's not been done on chip. But the issue we have is that we have this clock that is it's containable up to 4 to 5 gigahertz. 4 to 5 gigahertz, we have quite good performances. The clock is not too high, but starting from 6, 7, 8 gigahertz of input clock, and we start to see it like really prominent in the output. And one way that we have addressed this problem was to reduce as much as possible the input on the clock on this buffer. And we are thinking of techniques that if we could like even reduce it more, or even put the smallest offset to be able to just switch on and off this buffer, because as long as this buffer is switched, then it creates a full swing signal. So maybe we're going to try to, for the testing purposes, to reduce the amplitude and the swing of the clock, so we can have something that adds less defects, but at 8 gigahertz, even with the minimum setting in input power, we observe high clock presence in the RF output.
Okay, I think I will stop there for the.
Thank you for your questions.
Level questions, and I think I will leave the system level questions to the other. Thank you again for.
Thank you for your question.
Thank you, Antoine. So now, we give the floor to Brooke Smith.
Congratulations. I'm going to return to something you've already answered twice before. So we're going to talk about it for the third time. When I look at the total performance, it's actually a different question than I expected to answer this morning. Asked, when you look at the total performance, maybe the only disappointment would be the harmonic distortions first range.
Of course.
So let's talk about that, because it seems to be
the painful.
Right, exactly. So you seem convinced that the issue is synchronization in the sequences and not quantization of the coefficients or distortion of the DAC. Is that a true statement?
No.
I just want to get clarity on that.
No. The degradation in performance between the simulation is, in my opinion, the most based on mismatch. However, the overall
Mismatch of what? I'm trying to get clarity.
of the sequences, of everything, of the sequences between each other and of the DACs themselves. So is like the mismatch between the values of each DAC.
Okay,
So,
right, so I'm trying to separate it by plot.
okay.
So do you think the issue is with the synchronicity of the Walsh functions, or do you think the issue is within the DAC?
I think it's well shared between the both.
Okay,
Because with the sequences in schematic simulation with very simple DACs that I've used for first implementation, we already had a drop in performances, which was noticeable. And the real DAC only improved as well. So I think it's a bit of both, and both share a big responsibility when it comes to circuit performance.
okay. So I think your answer is I'm not actually certain which is the limit, or they could be equal, probably not.
No. I don't have the
Actually,
specific
certain
metrics from
limits
each of them,
Okay.
but just from what I've observed, it does even with perfect converters, the sequences themselves generate.
Right, so my next question is, have you looked at the SFDR performance as a function of frequency, input frequency? Not clock frequency, but input frequency.
Yes.
Is it better on the lower end or the higher end, or does it get significantly worse?
So we have this kind of simulation, I think, or in the first slides, and we've performed this simulation. So they were presented in here. So these are the linearity performances, simulated linearity performances, with a different input frequency. So the F Walsh is fixed and the input frequency changes. So there is a trend, usually, especially for, I think it's even more noticeable for, EVM performances, but we have it in linearity as well. There is a trend, as we can see, that obviously the frequency under 250 megahertz I wish as well, but we can see that it's still going down. But
Absolutely true, but what this speaks to an SFDR of around 40, and you're not achieving that. So
No.
I'm trying to figure out, and the difference between that
yes.
is it's a function of frequency.
So the frequency also increases this issue, as we saw in the simulation without calibration. We have huge amplitude mismatch, and even if we improve this mismatch in the generation, the sequence themselves are affected by the frequency. So the sequence at 8 gigahertz and the sequence at 250 gigahertz are not like proper multiple of each other. So the frequency in the sequence themselves is important, but for the input signal, to be completely fair, with different single tone signal, we've not had much improvement between a lower signal and a higher input signal. The main parameter is either the quantization or the clock, the main clock. If we reduce the main clock, we improve the performances. But if we look at the performances at 3 to 5, 4, close to the F Walsh and closer to the DC, the performance are quite similar.
Well, that's actually good news, because it might be that you can calibrate it at DC. It's a function of frequency, then that's a real problem. Because it's
Yes.
Yes. But if you can actually tune the synchronization at DC, then maybe you can get that thing back. I have other questions, but maybe we can talk about them more.
Okay, sure.
So,
Okay, thank you very much. So now I will give the floor to Isabelle, which is junior at semester manufacturing.
So first of all, one remark. Few years, so 25 years ago, this idea is right here, and it was a brilliant idea. It was an idea, and we transformed it in a silicon proof, which is very, very nice.
Thank you.
And the second thing is that a lot of questions have been done. I had a lot of questions about the design. It was the specificity of Antoine. So I would like to have another question, which is more in perspective,
Sure.
about the automotive radar. So in this approach, for the moment, you can generate a number of frequencies, so in the spectrum, simultaneously,
Yes.
while in the radar, in FMCW, we generate one frequency, but increasing the frequency instead of in a continuous way.
Yeah. So like a burst
So,
or
yeah, so you begin at, for instance, over the 4 gigahertz.
okay.
So you begin at the first, for instance, 2050, and then
Okay.
70, and so on and so on,
Okay.
up to 4, and then come back. How you can adapt this, because I think Walsh can do that. How you can adapt this system to generate certain frequencies.
So mathematically speaking or theoretically speaking, the circuit can technically generate any kind of signal at any time. However, I suppose that maybe in the radar application, maybe there is some sort of power level issue, and that can occur. So in theory, the circuit could generate right now signal, like we could do it in cadence later. However, maybe it could be optimized, because I don't know, like if multiple of frequency needs to be generated, or if every intermediate frequency needs to be generated. Maybe this type of architecture could be optimized to generate a certain set of frequency, and not every frequency in between. And it could be a bit scaled down in terms of reconfigurability and more in terms of application. So I think it could be like modified and simplified for burst generation and increased frequency if we do not require every frequency in any order. So this could be optimized.
It should be more frequency.
Yes. So maybe the number of sequences could be selected and dropped down. So we could use the same basis, but just remove some of the sequences themselves. So it will reduce the number of paths and improve and reduce the complexity of the circuit and improve the performances. And we could send any type of signal already, and just as we have missing sequences, it will do what we want. So yeah, it could be simplified.
So, any other questions was by the other members? So I do that. Thank you. Yeah.
Thank you for your question.
Thank you, Didier. So now, you know that Andrea Gattler was invited to this jury, and as she cannot come, she asked me to ask you some questions and comments and questions. So I will read the paper.
Okay.
So it's not my question. So I would like to thank the supervisors for the invitation to the jury and to highlight this work and to highlight this work is done in the frame of the ST-IMS Common Lab, so I can also did that. I would like to highlight the contribution and thank my colleague Sylvain Claire for his support on the digital design implementation methodology specific to the 28 ADSY from ST. And she also thank you for the work completed over the past 4 years on this thesis, the novelty of the proposed work and its implementation. So I will have some general questions. Can you please comment on the out-of-band behavior of this transmitter regarding to regulation and some mask emission that happen to be respected for the application?
Yes. So the out-of-band rejection was not like properly discussed in this job, as the first thing of this project was to generate a proof of concept. So obviously, when we start to speak with out-of-band generation, it's more of a mature product. However, so naturally, the architecture use square signals which have harmonics up to much higher frequency. So obviously, any disruption in these harmonics could disrupt the circuit itself. So out-of-band noise rejection is something important to study, but we have not studied for this work. But it would be an effect on the linearity of the circuit as well.
Another question, what direct benefit did you take from the DSOI technology? I think you already respond to this, and please do comment extensively on the usage of the body biasing for the same as linearization.
Well, it's the best technology of the world, obviously. So when it comes to the 28 nanometer, the really big upside was especially like it was a small technology. So when it comes to technology, it's not specific to FDSOI, but at least the 28 nanometer node itself was really beneficial for mixed signal design. So this is a big upside. And it helps reduce the consumption of the digital block as well. When it comes to the body biasing capability, we have not used them very extensively or very like smart in all of our design, because the two main reasons is that for digital parts, apart from the delay and sometimes the slow rate modification and the gain it can improve, there is no so many uses. And the downside of using the backgate for digital work, mainly, is that if we have our body that is biased, the end well of the transistor needs to be apart from any other end well which is not biased in the same way. So for digital application, we start biasing transistor individually. We start to have like issue in terms of area and spacing, and where we gain maybe in the gain by body biasing to counteract some effect of the process, we can lose it just because the transistor are so much far apart. So in the mix, however, it was still used in the DACs themselves as there are less transistors. So for the cascade transistors, some body bias was done in order to increase a little bit the gain to clean off the charge injection effect.
Maybe I will last one. What other kind of circuits, other than those for mobile communication PCX, can take benefit of such type of innovative solution using Walsh transform, and what would be the strong benefits?
So the strong benefit of this kind of architecture is mainly the wideband capability and the power consumption capability. So technically, we've designed a signal generator, and this type of architecture can generate any type of signal. So technically, we can use it for many applications. However, we can think it as different approach, as Mr. Bello mentioned, is that, of course, it's a signal generation approach, but it's also a frequency generation approach and an harmonic generation tool. So we can generate any types of harmonics, and the architecture can be optimized to generate specific harmonics. So if we are not talking about signal, we can, so maybe for clock measurement, it's not maybe well suited, but for harmonic generation, we can generate many harmonics in a large bandwidth, and we can simplify it to generate only specific harmonics. So it could be used for other types of applications like that.
Okay, thank you. So now I will let the floor to Daniela Tragurescu, who sent me some quick short questions. So thank you, Pierre, for the presentation. What is the reconfigurability capacity of the solution? In what range? And what is the positive impact on 5G from a system point of view, number of users, and so on? This is the first part of the question. And the second part is, I would like to have a more systemic view, the impact of its design on the capabilities of the 5G system.
Okay. Many questions in the.
You want me to?
Yeah, if you.
Yeah, the first one. What is the reconfigurability capacity and in what range and the positive impact on 5G on the system?
Okay. So when we talk about reconfigurability, I'm not sure if it's about performance reconfigurability or application reconfigurability or. Not sure.
This is a question for me.
Yes. I mean, reconfigurability, as we can generate like any type of signal, we can technically like use it for many use cases and it can be reconfigured. The reconfigurability approach could be to for filtering, for instance, to be able to have a filtering that follows the signal generation and that filters in bands and in between bands for this. So that would be like a reconfigurability things that will be present on the chip, but the design itself can be used for many applications and doesn't need to be reconfigured for different applications. We've decided to do the full Walsh, so it's any type of signal generation, but it can be like trimmed down to simpler application. But
And from a system point of view, regarding to the number of users, maybe there is also some benefits.
So yeah, technically, so it's a converter. So we are starting from the data itself, and we are wideband. So the main advantage is that we can technically address all the users at the same time, at the same band, which leads to simpler architectures. So that would be the main benefit in terms of system approach, is that it's one converter for them all, ideally. And that would be like the main advantage in terms of system, is that we do not have to have a specific system for each band. Only the passive, only the active analog components such as power amplifiers and antenna could be parallelized for different bands. But when it comes to the radio frequency front end without the amplifier themselves, they could technically be alone.
Thank you, Pierre, for these answers. So now we will move to the closest advisors of your PhD, and I will begin with Hervé at Yann.
Ça sera très bref, parce que je ne pose pas de questions.
Oui, c'est un anglais,
Je vais juste me contenter de vous féliciter pour la présentation, pour l'honnêteté de vos réponses. C'est un sujet assez simple. Et surtout, au-delà de ça, au-delà de votre thèse, pour toute l'aide que vous avez apportée dans l'équipe, aux invités.
Merci.
Thank you, Hervé. Yann Deval, the advisor of the thesis.
Thank you, Madam President. Well, thank you so much for this excellent presentation. It was really great, particularly on the side. And also thank you for the manuscript that is really, really easy to read from my point of view. Even if there is some part that have been read a little bit faster than others, and we were urged by the deadline of the official authority. I would like also to thank our colleagues for visiting us and reading the report, and also for the, let's say, outstanding advice that's coming from Doug regarding all these activities, and also more than that, actually. Thank you for what you have done, and the fact that from something which was an idea, you make a proof of concept. Of course, there is some work to do still, continue measuring that things, but also some, let's say, engineering to improve the quality. But the idea has been demonstrated, and this is your contribution, and this is a very important one for us regarding the Walsh signal generation. Thank you so much for that. I would have no questions because we discussed quite regularly since 4 years now. And just congratulations for what you have done. it was not so obvious to design that big chip alone. The layout, of course, you can do that better. But you have done that alone during the vacation of Christmas, not to mention.
And summer.
So it was a beautiful tour de force. Congratulations for that.
Thank you.
Thank you.
Thank you. And now we will finish with François, which is the main advisor of the thesis.
Merci Madame la Présidente. So first, I would like to thank all the jury members for being here today. My gratitude goes to my dear friends, Ramesh and Louis, who traveled all the way from the US to be here, and to Antoine and Didier, who traveled from far away from France to be here today for joining us. So today and tomorrow, can be a scientific exploration of Walsh theory in radio frequency communication, circuit and system. And for me, it's like a single coin with two sides. So the circuit and the system. And so today, we are on the side of the circuit. I would like just to say a few words about the history of all that. Because it began in 2011. A long time ago, when Jan and I were exploring the wideband transmitter concept. And in fact, so I said 2011, we were together dinner at Monaco. Well, the dinner ended quite late, but we had a very early flight to go to Brussels, to the European Defense Agency, so we had a nap, I would say, nice. And then on that trip, well, we experienced the pure French strike of the air traffic or so. Well, it was an adventure. And well, with the discussion we were a bit tired during the day, this is where the idea of generating sine waves with square waves began to take shape. And I remember with the taxi driving nearby the European Parliament, and then we started reading that, and within a few days, everything was sketched out. I mean, yeah, using square waves to make sine waves. But we needed a solid mathematical foundation for that. And we learned that just the beginning of it. And so Didier was definitely instrumental to support us because we secured several patents at that time without the Walsh things. But we had, I remember, 4 patents. And what I can remember, it was a very freezing day in Grenoble, with the mustache, one guy from the patent agency there. It's still there in my mind. 2012 for that, so 12 years ago. Yeah. And well, it took years of refinements, experimentation, and persistence. And when everything changed, is when we discussed with Duke. When Duke came in France for a visit in the Sahara region, Dordogne, he introduced us to revisit the Walsh function. And we say that he opened not the Pandora box, but the Walsh box. And everything was on the table. And then you sent me the paper Yarnay. I spent the whole weekend locked up at home, trying to understand what we could do with it, and that changed everything. Then, well, when I was in the theory, it was simple and complex at the same time, like the Walsh function, simple and complex. And then everything was aligned. Andrea took over from Didier, and then we were going for the first separate demonstration. Also in 2020, what helped us, the COVID, well, I would say everything changed. With the support from Didier at the CEA, we've written the project Alphabet 5 following Nano. And then with ST Microelectronics, supporting us with Andrea, we secured also the INR and then the European project. So it was 2 in 1. And I think maybe some students there can remember the time I was notified about the success of these projects. I was lecturing at the time. I received a text saying, okay, the project is started. I just screamed in the room and sent for the meeting there. Now, je switch to French et je voulais simplement dire que certains se souviennent du moment où ces projets ont été notifiés. Et là, c'était vraiment le début. What I will say, sorry, stop English. behind the scenes, we need good people to make this a reality, a proof of concept. Designing such circuits is like crafting a processor. And you can understand that a processor is highly complex. It requires meticulous customization, precise layouts of not 10 transistors, but tens of thousands of transistors, all by hand. This is craftsmanship at its finest, a blend of art and engineering. And so, now we go back to French. Nous cherchons qui pouvait faire ce circuit. Et ça, c'est la fin de la partie 1, c'est bien. We have part 2 tomorrow. Donc, en 2020, nous sortons tout juste du Covid, et Pierre faisait un stage à Toulouse sur la 5G. Vous avez accepté de vous lancer dans la conception de ce circuit. Ce n'était pas forcément ce que vous faisiez en stage, mais vous aviez le label 5G sur. Et je me souviens encore du challenge que vous avez fixé pour votre première année, faire un layout à la fin de la première année. D'où le premier été passé au laboratoire. Alors c'est un peu en mode de crash test, un petit peu comme une fusée SpaceX, on voit, on essaye, hop, on met la route, et on voit ça. Alors, justement, ce qu'on peut dire de travaux, c'est que ça a été une aventure. De la première minute à la toute dernière minute. Et ce que je répète souvent, c'est tout ce qui peut aller mal a été mal.
Je suis superstitieux maintenant.
C'est de l'adversité, et on a su trouver quand même chaque fois des solutions. Alors je vais faire la petite liste, le CMP qui ferme pendant 2 ans, donc impossibilité de faire travailler ça. Des design kits qui n'arrivent pas un jour, un papier journal qui n'a jamais été reculé.
Si, il a été reculé au bout d'un an.
L'intégration de la spécialité sans les outils pour le faire au début, comprendre l'extrême complexité, l'erreur dans la taille du packaging du circuit dont on est maintenant au courant. Et là, j'aborde sur les dernières minutes, impossibilité de faire fabriquer le PCB. Je me rapproche encore de la dernière minute où on a eu des retards de livraison, des circuits qui claquent, les uns après les autres. L'ultime, c'est quand Pierre veut venir mesurer son circuit, c'était il y a 10 jours, panne générale, et testé sur toute la lance. Voilà. Bon. Et malgré tout ça, vous avez survécu, et je pourrais même dire que vous avez eu la chance d'apprendre de tous les risques qu'il faut savoir maîtriser et anticiper. Alors j'ai pu apprécier votre calme olympien, malgré tout ça, votre persévérance, voire même, je dirais, la maîtrise de vos émotions. On l'a très bien senti aujourd'hui d'ailleurs. Avec cette phrase, j'aime bien parce que à chaque fois qu'on m'appelle, on dit « Ah, François, là, et je me dis « Allez, on est parti pour un tour. » Ce que je tiens à noter particulièrement, c'est que vous avez beaucoup évolué en 4 ans. Vraiment. J'ai pu voir que vous avez acquis une grande maturité dans vos connaissances. Alors, en conception de circuit, ça s'est senti vraiment aujourd'hui. Vous savez ce que vous faites. En méthodologie et aussi en rédaction, ça, j'ai pu le sentir à l'écriture de la thèse. Le premier chapitre écrit, je vous là, maîtrisiez l'âge de l'écriture de la thèse. C'est pour ça que je pourrais dire que la persévérance a payé. Alors maintenant, comment ça se traduit? C'est qu'on vous demande conseil. Alors, ça, la conception, c'est vous le référentiel. Personne qu'on va voir pour demander des petits trucs et astuces, ce qu'il faut faire. Ça, je pense que c'est la plus grande récompense. Et votre expérience est essentielle pour sécuriser les projets, je veux dire, de l'équipe, mais des équipes de conception de circuits ici au laboratoire. Pour ça, je veux dire, on peut rajouter à tout ce qui peut aller mal a été mal, mais c'est un mal pour un bien. Bref, vous avez gagné vos gars. Alors, on est enfin au bout d'un long chemin. Ce type de travaux, on a pu dire, est d'une très grande complexité, aussi bien dans les mathématiques, qu'il faut appréhender, que dans la conception, ici, analogique, numérique, RF, bien total. Mais aussi dans la démonstration, c'est une fois. C'est pourquoi je vous félicite pour avoir réussi à mener à bien ces travaux et même d'avoir su en capter l'essence. Merci.
Merci François.
Thank you, Mr. Rivet. So, for me, there is no more question, but just I want to thank you for the work done. François talked about the Nano 2022 project that you worked on, and also on the ST-IMS Common Lab frame, and your participation to the workshop and on the stuff associated to the Common Lab. So thank you again for your contribution in this field. So now the jury members will discuss about your performance in a few minutes, and then we will go back with the result of the session, our discussions.
Thank you.
la mise en œuvre d'architecture système, la maîtrise des outils de simulation et la caractérisation des circuits. Vous avez démontré également une connaissance solide et une compréhension de la technologie 28 nanomètres CMOS FDSOI et son utilisation dans le cadre d'une collaboration avec l'entreprise ST Microelectronics. Vous avez pu démontrer la pertinence de ces architectures, donc d'une idée très originale et très innovante. Vous avez créé un prototype et vous avez montré que ces idées innovantes pouvaient prendre réalité. Le jury a aussi apprécié la qualité des échanges qui ont suivi la présentation. Les réponses aux nombreuses questions du jury étaient claires et argumentées, qui mettent en avant la maîtrise de votre sujet et le recul que vous avez pu acquérir. Et l'ensemble des réponses aux questions et de la présentation ont bien complémenté le manuscrit que vous avez rédigé. Devant cette qualité à la fois de la soutenance et des réponses aux questions, le jury a décidé de vous proposer, pour l'obtention du grade de docteur de l'Université de Bordeaux, dans la discipline physique et sciences de l'ingénieur, dans la spécialité électronique. Donc, félicitations, Monsieur Ferrer.
Merci.
Alors, en dernier petit travail, Pierre, après la décision d'admission, nous te proposons, c'est une proposition, de lire le serment du docteur.
J'accepte.
En français ou en anglais, et donc je te donne le papier, il faudra me le rendre après.
En présence de mes pairs, parvenus à l'issue de mon doctorat en électronique et ayant ainsi pratiqué, dans ma quête du savoir, l'exercice d'une recherche scientifique exigeante, en cultivant la rigueur intellectuelle, la réflexivité éthique et dans le respect des principes de l'intégrité scientifique, je m'engage, pour ce qui dépendra de moi, dans la suite de ma carrière professionnelle, quel qu'en soit le secteur ou le domaine d'activité, à maintenir une conduite intègre dans mon rapport au savoir, mes méthodes et mes résultats.
Je laisse prendre la parole si tu as des mots à rajouter.
Merci, Madame la Présidente.
Merci.
So I first like to thank the reviewer and everyone that came to review my work and discuss about my work. Your feedback were so much appreciated, and it's really nice to discuss with people that are interested in what we are doing. I will now switch to French. Yann, Hervé, François, merci mille fois parce que vous m'avez accompagné de A à Z dans ce travail qui a été plus dur et plus long que ce que j'imaginais. Donc, je vous remercie pour toute votre participation, autant intellectuelle que humaine. Et bon, sans faire de jaloux, je tiens quand même à remercier François également, énormément et plus spécifiquement, puisque vous m'avez le plus suivi, vous avez le plus été là pour moi. Surtout dans la dernière ligne droite, qui a été très dure psychologiquement avec tous les travers que j'ai eus. Donc, je vous remercie pour vos idées, pour vos propositions constantes dans ce qui est de la réalisation de ces travaux et pour votre soutien et votre confiance en moi aussi, qui a beaucoup compté, puisque parfois vous aviez plus confiance en mes capacités que moi-même, donc ça faisait plaisir. Je tiens à remercier évidemment toutes les personnes qui sont ici aujourd'hui, donc tous mes collègues de travail et donc mes amis pour la plupart. Je vous remercie vraiment d'avoir été là tout le long. C'est avec vous que j'étais heureux de venir au labo. Et je ne viens pas au travail, je viens aussi voir mes amis quand je viens le matin. Donc c'est un plaisir. Je vous remercie tous d'être là. Et je remercie aussi mes amis qui ne sont pas au labo, déjà d'être venus, d'avoir subi ça. Et de me soutenir, de me faire rire et de me faire penser à autre chose que j'en ai marre de ce circuit. Donc c'est un plaisir et je suis hyper heureux de vous avoir autour de moi. Et puis je remercie évidemment mes parents qui m'ont toujours soutenu et toujours incité à aller loin dans les études et à ne pas me restreindre en ce qui concernait ça. Et évidemment, j'ai une grosse pensée à Camille qui n'a pas pu être là aujourd'hui, donc je la remercie pour son soutien, pour sa tendresse envers moi et pour sa patience. Voilà. Donc je vous remercie à tous. C'était un plaisir de passer ces 4 années à vos côtés. Tu veux vos photos?
Ouais. Pour, oui, petite photo. Donc, Thomas est là, on va se mettre autour de toi.
Ouais.
Moi, je me suis mise en couleur pour prendre. Thomas, c'est le garçon qui a. Mais mets-toi, oui,